In this video, I want to take a look at a couple of examples of Euler's method and zoom in on what can go right and what can go wrong. So here we go. First example is an autonomous equation. So this is like logistic growth, but it's upside down instead of a 1 minus y over 5 here. I have a y minus 5, so I have equilibrium values at 0 and at 5, but it's headed downhill away from that upper one. Anyway, it's like logistic growth, but upside down. The thing that I want to do here is I want to take a look at Euler's method with an initial condition of 0, 4, and I'm going to start off with h equals 1 and see what's going on here. I actually solved this ahead of time, and I know this is the solution that passes through the point 0, 4. So on my graph here I can see both the estimated values and the black curve being the actual values. I notice just at this level that it looks like initially I start getting off here. So I'm gonna zoom in and take a closer look here. What I see is that initially of course the curve is bending downward, but my tangent line goes straight to get me over to this first guess here, my first approximation. So I know that's going to be wrong. And I know it's going to be above the actual answer because this is bending downward. And then the next one, of course, is off by a little more. But what happens at this point is that this one actually gets me back closer. The curve starts bending back upward, and so that fact that I was above it corrects itself here. And in fact, I end up on the next step being below the curve. So where I was erring on the high side, I'm now erring on the low side. And then it all sort of works itself out because of the nature of this equilibrium value, that y equals 0 is a stable equilibrium value. So all my solutions are being funneled into becoming very close to 0. And so my estimated y values here are actually getting very, very close to the real y values because, well, everything's being funneled into 0. So we're getting very close to the correct answers. But I find it interesting how the change in inflection caused estimates that were too big to become estimates that were too low. Right? So the nature of the curves here determined I didn't keep getting worse and worse approximations. I actually got better for a moment and then worse on the other side. And then the nature of the differential equation then was pulling everything back in to being accurate again. Okay. Now, I want to take a look at a couple other things real quick. With h equal to 3, I get kind of an interesting thing going on here. I mean, h equals 3 is big. We really wouldn't want to do that, but just you can see the first guess is too high, and then the next is too low, and the third point then is way too high, but it's still less than 5. And so the nature of this differential equation is it pulls it back down again. This should be approaching 0. Again, it drops below, it goes above, drops. You keep getting this sort of random up and downness. Still not going off too crazy, but it's kind of a funny up and down. The other thing I want to do, I want to point out that, so let's go small. Let's actually take a small step size, 0.01, and see what's happening here. Let me zoom in and zoom in a little more. I'm just trying to see, am I too big or too small? I think I can see that. I mean, I'm expecting with this bending downwards that my estimates on the y values should be too big, which in fact they are. But we get to the point where the curve is concave up, and then those points should come back to being Getting closer and closer. In fact, you get back to being, looks like pretty much right on the curve there. And then you start to error on the low side because the curve is bending upward. But then the differential equation starts taking over and everything's being funneled into zero, and this will again get very accurate, get back right onto that solution curve. Okay, or maybe not right onto it, but so close that you can't tell the difference, right? So anyway, there is that example. Let's now move on to a different example. In this example, we have y prime equals minus t over y. Now we've done this one, solved it. This is separable. The solution curves look like circles. They are circles. So I'm starting this one with initial condition of 0, 4. And so I'd be on the circle of radius 4, which the solution curve here is y equals the square root of 16 minus t squared. And you can see that in black here. Okay. Now I've got 20 points plotted. Because this is bending downward, I would expect that these solutions are actually on the high side, right? That if I zoom in, I should see that the y values of my estimated points are actually higher than the circle. And this never gets better because it doesn't bend the other way. It doesn't ever become concave up. However, let's plot a few more points here rather than 20. How about let's go with 40 so I can see what's going on. Yes, in fact, this keeps getting, the y values keep getting further and further away from being correct. Okay. So the thing that I really wanted to show you here, though, is not so much that, but what happens. So with 40 points, doing a step of 0.1, I'm only getting out to 4. So as you can see, I should be down at 0, and I'm up here almost at 1 for my y value there. So I've wandered off from the actual solution. But let's do a few more points, because this would actually get me beyond the domain of my solution curve. So for some reason the recording has stopped. I'm not going to worry about it. I've been fighting with this all afternoon. So here we go. You get the audio. When I go to 40, let's go up to 60 points, that the next point suddenly is too far down below 0, and then these are pointing upward, which then puts you up there, and then down here. And what's happening is you're following other solution curves that once I get sent down here, there's a circle that's bringing me back up to here. Well, then that sends me probably even way up way up here, and then it's starting to follow down there. So yeah, I am still within the domain of the differential equation function, right? The minus t over y. But I'm not within the domain of my solution curve. So I'm jumping off onto other solution curves and then just following those until I get sent to some other place. So yeah, the Euler's method, depending on the nature of the differential equation, can do some really crazy stuff.